Okay, thanks for coming to watch my talk. I'm going to talk about sampling and integration of Logconcave functions. This is joint work with Santosh Vempala. Let me start with some conceptual connection between Logconcave sampling and convex optimization. You can think of Logconcave sampling, roughly speaking, as like some sampling counterpart of convex optimization, because like analysis and algorithmic designs of convex optimization have motivated like Logconcave sampling literature, and also if you're able to sample from e to the minus v, then you can do optimization of the convex function v as well. And just as convex function include a lot of important family of functions, Logconcave distribution also include a lot of important family of distribution, such as some indicator function of convex set, some exponential distributions, and Gaussian distribution. So hopefully this slide motivate you enough about Logconcave sampling. And before getting into like our main result, the Logconcave sampling problem, let me just start with some simpler case, but important case, which is convex-wise sampling. Because indicator function of convex set is Logconcave distribution, so convex-wise sampling is a special case of Logconcave sampling indeed. So here is the computation model. So our computation model is membership oracle, which tell you if you query point X, then this membership oracle tell you if X is in K or not. And then for a regularity of K, so we typically assume this K contains some unit ball, and also it has diameter D, like this. But actually often, this is generalized to some second moment condition like this. And in this computation model, our question is how to sample approximate from the uniform distribution phi, and also like how many queries do we need to generate some sample X, which is epsilon close to phi in some chosen metric D, and D could be anything you want, like TV distance and KL and chi-square. And before going over some guarantees and previous work on this problem, let me just remind you about the hierarchy of this probability divergence and distance. So ranking Q divergence is perhaps the most general thing that encompasses all the things showing up here. Ranking Q is known to be increasing in Q, so ranking infinity is the strongest, which is essentially just essential supremum of log of the ratio of two densities. And then ranking 2 has connection to chi-square through this equality, and then ranking Q goes to KO, and then this should be understood as a limit. And then KL implies TV square as the well-known Pinsker inequality, and KL implies 2 Wasserstein square as by the T2 Talagrans inequality. Okay, now we are ready to state the complex of uniform sampling. So in this setup, we typically assume we are given some initial distribution phi 0, which is an M worm with respect to phi, which really means some pointwise bound on this, the ratio of two densities bounded by M. And throughout this talk, I'm often saying like ranking infinity is bound, in a sense that because ranking infinity is equal to log of some the ratio, so M worm really means like ranking infinity bound. Ranking infinity distance between mu and phi 0 and phi is bounded by e to the m. And a known result about this uniform sampling is this. So you can achieve epsilon closeness in ranking Q divergence using this many queries. So you have linear dependence in Q and M, but quadratic dependence in dimension. And here lambda refers to the largest eigenvalue of covariance matrix of phi. And later on, it is also known that you can achieve ranking infinity bounds between these two distributions using this many queries. So now here, so instead of lambda, now you have r squared, the second moment term here. And as a quick side note, this ranking Q guarantee follows from some Poincare constant of phi, the target distribution phi, whereas this ranking infinity bound comes from some LSI, log overlap inequality for this target distribution phi. So the next question is, how can you achieve some warm start, like O1 warm start? Because in the previous slide, we saw that like this, every like either RQ and R infinity guarantee has dependence on this M, the warmness. So in order to achieve a tractable complexity, so you want to achieve some O1 bound on this warmness, right? And then the answer is by Kook and Vempala. And also there are some refined question by Kook and Zhang. So you can basically using this many samples, n squared times n maximum of n and r squared, you can find some sample x which is a O1 close to phi in random infinity. So we're good. And the next question is like how to make this phi near isotropic. So near isotropic means the covariance of phi is roughly close to identity matrix. And the question, the reason why we care about this question is the Curry complexity of uniform sampling has dependence on lambda or r squared as well. But if your convex body K is highly skewed, lambda or r squared either could be very large, so your sampler might suffer from poor mixing. So that's why you want to make sure like phi is close to identity. In such a case, lambda would be 1, and the r squared going to be n. And this question, like an isotropic rounding question, can be translated in a slightly different question, which is how can you estimate covariance of phi as accurately as possible? Which is like you want to estimate sigma hat such that with probability say some constant like 0.9, your estimate is fall under very close to this actual phi, the covariance of phi. So the reason is if you're able to sample mu, the mean and covariance pretty accurately, then through this affine transformation, you can make sure the push forward distribution through this F is very close to isotropic uniform distribution. And also you can boost up this probability as much as you want by spending some log more curries. This is very standard technique by taking some sort of median stuff. So let me just go skip it. So yeah, for this question, there's all your work showing that there is some selection algorithm using this many curries. The last question that I want to go over is volume computation, which is a pretty fundamental and classical algorithmic problem that has been studied since like 1990. So in the same setting, in the computation model, you have some target accuracy epsilon. And the question is, how many curries do we need to achieve a pretty accurate estimation of volume, K? So which means this equality. And so once again, you can boost up this success probability as much as you want, as close as to 1. And the here answer is, first of all, we may assume that your body is well-rounded, which really means this second moment is bounded by ON, which is, so this is more general condition than just isotropy. And also we can assume such a thing because of the isotropic rounding that use n 0.5 time polylog r curries. So for such a well-rounded body, there is this algorithm using n cubic over epsilon squared curries to solve this problem, the volume computation problem. And then, yeah, as a quick corollary, by combining this with rounding algorithms, we can do volume computation using this many curries in total. Okay, so here, this is a summary of all the 4 problems that we have gone over so far. But now, let me show you this main result of our talk, main paper. So uniform sampling can be generalized to Logconcave sampling. And for this problem, we can extend this result to this log-concave setting like this. The only difference is that we have like some kind of maximum of lambda with 1 here. This is the only difference. And then for Wurm's generation, we can achieve the same complexity as the uniform sampling case. And for isotopic rounding, and we can also achieve the same complexity. And then generalization of volume computation can be thought of as like integration. And then for this task, we can also achieve the same complexity. And then before this work, like in 2016, by Lovaas and Vempala, they use some hit and run algorithms, which is very classical random walk style algorithms. And they show that some several results on this problem as well, but always worse than our guarantees. So now let me just start with our main topic, log-concave sampling. So I should start with our computation model, what this is. So we work with evaluation oracle, which can be thought of as a proper generalization of membership oracle model that was used for uniform sampling. So here, let's say f is integrable and log-concave, so that you can write f as e to the minus v for some convex function v. And then phi is some log-concave distribution whose density is proportional to f. And then here, just as we assume like K contains some unipole, and then it has second moment bound by R squared, the first condition is translated to slightly different condition, but still generalize this condition. So here, let me call it just ground set, which is defined as this way. You just collect all the point whose points such that like v of x is within like 10n from the minimum of v, and then we assume ground set contains this unipole, and then also assume second moment condition. And then this evaluation oracle can tell you that like if you carry point x to this evaluation oracle, then this oracle tell you the value of vx. And yeah, our question is the same. Like in this computation model, how many queries do we need to generate sample x, which is close to phi, in some chosen metric d and chosen accuracy epsilon. And then like instead of hit and run that was used in Lovaas and Vempala's work, we are going to use proximal sampler, which is some kind of general sampling framework. How it works is the following. So say like phi x, phi to the x is proportional to e to minus v, which is track distribution. And then say h is our step size. Then this framework considers some augmented distribution over Rn times Rn space, given by this, which is simply just multiplication of original target times some Gaussian center at y. And then one iteration of proximal sampler just alternates these two steps, forward step and backward step. You basically do just conditional sampling for y and for x. And the fourth step is pretty easy to implement because this is simply just Gaussian distribution centered at xi. But however, the backward step is non-trivial to implement. But you can still do implement for some sufficiently regular distribution. For example, when your potential function v is some gradient ellipsis. But in our computation model, pretty like general computation model, we have no idea how to implement this backward step. And to get around this issue, we go back to convex optimization, which has been the source of some algorithms and analysis of sampling algorithms. So in convex optimization, a convex function, the potential function is typically replaced by some auxiliary variable t. And then like just epigraph, which is convex, is appended to constraint. So you can essentially, so instead of directly solving this question, people sometimes like work with this formulation of this problem. And then we basically use the same technique for log-concave sampling. So instead of directly sampling from this e to the minus v distribution, you basically do the same thing. Like you just replace V by some NT. You have some coefficient here for some reason, technical reasons. And then you just replace, now you work with some exponential distribution like this, but truncated to some convex set. And yeah, you can easily check that like phi x is x marginal of this augmented, like lifted distribution, so that all you need to do is just sample from this augmented distribution and then just discard t part, only keeping this x part. Then you're done. So roughly, like essentially, you just do the sampling from one-dimensional higher space. So yeah, now denoting the the augmented space as z, and your augmented distribution now look like this. The benefit of this approach is now very obvious because now your backward distribution can be written in a clean way, like a truncated Gaussian. So yeah, now you just use the rejection sampling with proposal this one without this truncation, and then you just accept the proposal from this Gaussian until your proposal lies in this K. And then this is summary of pictorial illustration of our approach. When you're given some Logconcave distribution like this, you just go one dimension higher space, in which your potential now is very simple, and then you just run proximal sampler on this n+1 dimensional space. So yeah, and so far so good, but it might be very convincing that our approach is very conceptually acceptable. But in order to get a concrete complex debound, we need to understand this process more specifically with details. And some earlier work by Chen et al. Showed that the proximal sampler can achieve epsilon closeness in Rennie-Q divergence after this many iteration. So here H is step size, and this CPI is Poincare constant of your target distribution phi x. And yeah, and then this consequence is basically comes from some strong data, a better understanding of strong data processing quality under heap flow. And then you can take a look at this work if you want to understand this as DPI in a deeper way. So yeah, now with this given guarantees, we now have two concrete questions. So now that we work in n+1 dimensional space to sample from phi of x comma t instead of directly sampling from this phi x, we have to understand the Poincare constant of this augmented distribution, lifted distribution, not just phi x, right? And then the next question is how large h could be, right? Because larger h means the better mixing time. But of course, you cannot take h step size h too large, because if you take h too large, then the complexity of the backward step implementation by rejection sampling could be very bad as well. So for the first question, we show in our paper that the largest eigenvalue of covariance of the lifted distribution is bounded by maximum of 1 and this original covariance matrix, largest eigenvalue of covariance matrix. And then using the known bound on the Poincare constant for Logconcave measures, we can show that this Poincare constant of the lifted distribution is bounded by log of n times this maximum of 1 and largest eigenvalue of covariance of phi of x. And then h, we show that h can be as large as 1/n squared roughly, in order to ensure O tilde m, here m is warmness, m complex to backward step. So by multiplying these two m Curry complexity for backward step, and then require number of iterations for achieving epsilon closeness, you can obtain this Curry complexity. And as compared to uniform sampling guarantee, the only difference is you now have this part. You have additive like n squared term here. So yeah, so we just covered the first line here. We have another result for achieving a random infinity guarantee, but we skipped this result in this talk. And now let's move on to worm star generation. So yeah, so like I already mentioned earlier, we have like linear dependence on M. So we want to find some good worm star, which is O1 worm star, such that like random infinity between law of z and with respect to phi is O1. And then previous common approach is annealing, which is simply speaking, we just follow some sequence of distribution, mu0 to mu k, which is kind of gradual transition from mu0 to phi. And then there is some condition that you want to ensure to obtain some tractable algorithm. The first thing is mu0 should be easy distribution so that you can easily hop into this annealing scheme. And also mu I plus 1 should be close to mu I, because mu I is going to be used as a worm star for mu I plus 1. And then it turns out like Gaussian annealing is a pretty standard approach for generating a worm star for the uniform distribution, which really means this annealing distribution mu I is simply some truncated Gaussian, okay, with the sigma I squared, the variance term, increasing according to some suitable schedule, which I'll tell you in more detail in later slide. So yeah, and motivated by this approach for a general Logconcave distribution, you might think like it's very worth considering this annealing distribution. You just simply multiply 5 times some Gaussian. But once again, we don't know like how to sample from this multiplied distribution. So once again, we take the like exponential lifting approach by replacing v by some nt and then truncate it to some k, right? So yeah, our approach in general is just you want to generate a worm star for this lifted distribution, and then now here annealing distribution is given by this. So you have, as compared to like Gaussian annealing for uniform distribution, now we have like 2 parameters, sigma I and low I and sigma I squared. So we call it like tilted Gaussian annealing because you also have like you have the tilt exponential term as well. Yeah, and once again we use the proximal sampler to sample from this. And then here is the algorithms. You just start with this specific choice of parameters in order to ensure you can easily jump into this the beginning of phase 1 by rejection sampling. And then in phase 1, you just simultaneously update low I and sigma I squared by multiplying by the same rate, which is 1 plus 1 over n. And then in phase 2, you just kind of accelerate your the multiplication by this. And in phase 2, your low I is always fixed as, say, n. And let me give you like some theoretical guarantees of tilted Gaussian annealing. First of all, as desired, mu I and mu I plus 1 are O1 close in random infinity. So mu I actually is a good worm start for mu I plus 1. And then proximal sampler's complexity for sampling from mu I, the annealing distribution, is roughly n squared times the maximum of 1n sigma I squared from O1 worm start. And then for the phase 1, its total complexity is n cubic. This is because the multiplication here is 1 over n, so doubling of low I and sigma I squared take roughly n phases, right? N inner phases, and also each phase takes n squared curry according to this result, so that n squared times n simply give you n cubic curries here. And then for the phase 2, you have n squared times r squared total Curry complexity, because here in this regime, each interface take n squared sigma I squared Curries, while doubling of sigma I initial sigma I squared takes r squared over sigma I square. So by multiplying this, each doubling of sigma I squared take n squared r squared. And because there are like log of r squared many doubling phases, so that we have the total complexity of n squared r squared for the phase 2. Yeah, in the last phase, and at the end of like this annealing phase, you should finally jump out of this annealing scheme and then go to phi, your target distribution. And here, using our second result, which I skipped, you can achieve n squared r squared Curry complexity in total. Yeah. So here's a summary. So annealing through tilted Gaussian takes this many Curries, and sampling in the last phase also takes this many Curries. So putting them together, combining them together, we have this many total Curries for O1 Warmstadt generation. So now second part is done. So and then let's move on to isotropic rounding. So yeah, as I already elaborated for the isotropic rounding of Yunbum distribution, we're going to estimate the actual covariance of phi as accurately as possible through this relation. And then our approach here is we basically generalize some approach ideas in this paper with some technical refinements. Roughly speaking, we just repeat like this simple idea. We just draw samples, a few samples, not like many samples, and then based on this like small number of samples, you have a rough estimation which could be roughly right in some direction but very wrong for some other directions. And then based on that, you can based on this rough estimated covariance, by running some SVD, you can kind of detect some skewed directions. And once you identify just such a skewed direction, you just double that direction, that axis, and then you just keep on repeating. And this is the overall idea of their idea. Yeah. And yeah, here is some pictorial example illustration of this idea. You just sample from it, and then estimated some rough covariance, and then just upscale this direction. Yeah. So to make more concrete about our idea for Logconcave distribution. So instead of directly rounding phi, we first consider this grounded distribution, which is you just truncate this target distribution to this ground set, because this will streamline our analysis pretty significantly. And then let's also define nu r, which is a truncated distribution, truncation of nu, the ground distribution, to a ball of radius r. And then here is our plan. So we just sequentially isotropize this sequence of distribution. You start from nu 1, and then you increase a ball here, the truncation ball, to r, to ensure you include all the most of things of your nu ground distribution. And then you go from nu r to nu, the ground distribution, and then finally go to from nu to phi, your target. And here the rate of this update is 1 plus 1 over n. So roughly speaking, we just kind of hand over isotropic from one distribution to next distribution in this sequence. Yeah, so we already took a look at the outer loop of this approach. But So now let's move on to inner loop, which is about, I'll call it sampling and rounding. So here the input is some invertible affine map between Rn such that given some, say, under this affine map, your push forward measure is a near isotropic, and your output is some new affine map prime such that your next, in this case, nu r squared time. Your next distribution with respect to this new affine map is near isotropic. And so by running inner loop for each of these pair, so we can successfully passing this isotropic from one to next, right? And then one of our results is the sampling rounding takes like n cubic curries, and because like there are like square root n many iteration in our loop, so we need n to the 3.5 curries in total. So let me be more specific about this inner loop algorithms. So let's say R is the largest radius of the ball in the ground set. And then you just keep on repeating this loop. You first sample like this distribution, R square many point. And then you just estimate the empirical mean and covariance through this quantity. Oops. Yeah. And then you just, like us explained earlier, you just run SVD to detect some eigenvalue and eigenvectors such that you just first identify some eigenvectors whose corresponding eigenvalue is smaller than n, and then you just double it those skewed subspaces, and then you go back to this first line with R replaced by 2R, so that like this while loop will finish in log this many iterations, right? So here, just let me give you some series of some theoretical lemma, the result on this algorithm. First of all, so when f, this f like push forward the measure of nu r, is when this is near isotropic, the push forward measure of the next distribution is well rounded, which means the second moment is on, and its ground set also contain an unipole. So in other words, your next distribution is not that like skewed. So because of this condition, like uniform containment and then where round is, you can just use our earlier tilted Gaussian cooling. We can generate a warm start using n cubic curries, right? And also because of this condition, the largest eigenvalue of covariance is obviously bounded by n. And then the first line will use n squared time lambda many curries. Of course, this sampling task will be done after exponential lifting approach. And then complexity of each sample is this one. And because we sample at R squared many point, so we will have n squared lambda many curries in total. So you might be wonder why we have like some R to the minus 2 terms here. The reason is now the ground set have contained a ball of radius r. You can take like some, roughly speaking, you can just scale it by 1 over r, and under which your covariance also, your largest eigenvalue of the covariance matrix also scaled by 1 over r squared. So that's why you have this additional r squared term here. And then second line ensures some this relation. And then and then in the third line we just double this some skewed subspace, and it turns out this indeed makes the inner largest radius r like 1 minus something like ish. So it almost double the inner radius. So this really justifies our the first line, which says we goes back to the first line with the r replaced by 2r. And furthermore, we already note that like lambda start with on, right? And then it turns out like this doubling scheme only increase lambda by additive n. So that, and then since there are like log of m many iterations, a while loop in total, so your lambda, your largest eigenvalue of covariance matrix, will remain as O of n throughout this algorithm. Yeah, so in lemma 2, we said the sampling step takes n squared times lambda many curries for each loop, and because lambda remain as O of n throughout, so we have like n cubic curries in total. So this justify the n cubic complexity of the inner loop sampling and rounding. Yeah, now let's move on to like our final problem, integration. So yeah, this is our question. You wanna just approximate integral of f as close as possible in a multiplicative way. And then our approach is to generalize all your ideas for volume computation with some statistical streamlined statistical analysis. And here is our high-level idea. And just as in annealing and just as in like isotropic rounding, we also follow some sequence of integrable Logconcave functions and moving across mu I whose density is proportional to fi, and then we will do some sampling to draw some samples from mu I and then do some estimation. And the sampling task is once again done after exponential lifting and then use the proximal sampler again. And then this sequence will be designed in a way that f1 is easy to integrate, and then mu I will be a O1 when we start from mu I plus 1. And furthermore, chi-square of mu I plus 1 with respect to mu I is bounded by 1 over m. Here m is just the number of phases. And then equivalent formulation of the story condition is simply the variance of estimator of this one with respect to mu I is simply this one. So we will use this condition later on. And it turns out the annealing distribution that we use for using tilted Gaussian annealing still serve as a good choice. So because we can easily check that like expectation of EI is simply the ratio of two integrals, we can write down our target quantity integral phi, integral of f, as a telescoping product of this in this way, right? Because this one is f2, and then this one is final quantity. So we'll have like nice cancellation, and then we finally reach the desired quantity, which will match this quantity, integral of f. So yeah, so it is very convincing to use this quantity as our estimator of this quantity, right? But there's some catch. If all samples used in this estimation are independent, the estimator of this, our estimator will be the unbiased estimator of our target quantity, right? And then since the variance of this one, which is enforced by our third condition, which is this, by using independence and using just doing the basic probability algebra, we can check that variance of our estimator will be given as this. And then using just Chebyshev inequality, we can argue some concentration of estimator around the mean, which is our target quantity, right? If every sample used are independent. But however, as you already are aware, our samples are actually dependent, because when mu I plus 1 is sampled through a proximal sampler, we use mu I, the previous sample, xi, as a warm start, right? And so that our estimator is not really unbiased, in fact biased, right? And even worse, our samples obtained by MCMC samplers are in general approximately distributed, right? You can ensure running as many as iteration we want. You can ensure this distance is as small as possible, but this doesn't really mean that the final law is exactly equal to your target, right? So you have two issues: dependent issue and approximate nature of your samples, right? And then all the previous work used some coupling argument, which is also referred to as some divine intervention in earlier work, and also used some notion of alpha mixing, which was called mu independence in earlier work. Earlier work used these two techniques to address these two issues, but their approach, this analysis hacks are not actually clean, pretty involved in some way. So we try to streamline those analyses in this paper. So yeah. So the way we streamline the analysis, statistical analysis, is to show assuming independence is not too bad. Actually, it's almost okay. So first of all, the approximate law issue could be addressed pretty in a simple way. Say bar mu I is actual law of xi satisfying this one. And then you can easily check that the random infinity of tensor product of mu bar I and then tensor product of mu I is also bounded by epsilon. So the probability of any event with respect to this bias distribution instead of the dependent the target distribution increase only by a factor of 1 plus epsilon. And then the dependence issue is addressed by relying on the notion of beta mixing, which measures some deviation between joint law of xi plus 1 with respect to the tensor product of these two independent distribution. So in our paper, we show that this beta can be bounded by epsilon over m using this known quality. And then when analyzing any event, we can replace this independent event, independent reference measured by the actual dependent joint law by only at the cost of this additive cost of epsilon, right? So the overall approach is that first do the analysis with respect to independent distribution, and then have some beta probability. Suppose you bound a beta probability by 0.1, and then by changing the reference measure from here to approximate distribution, maybe this goes up to 0.2. And then you just replace this once again to this actual dependent distribution. Then you just, then 0.2, this bad probability goes up to 0.3. In such a way, we can significantly streamline the statistical analysis of this algorithm. So yeah, here is a summary of all the problems considered in this talk. For Logconcave sampling and warm generation, isotropic rounding, and integration. And then as you see on the left side, our algorithm, our result exactly generalized of this uniform case to this log concave case, only up to some additive curves. And yeah, and thanks for watching the talk.